Welcome to the 2025 Open Air Carbon Removal Challenge Final Showcase. My name is Matt Parker. I'm the co-founder of the Open Air Collective. This is our third annual challenge. It's the only annual challenge for higher ed students to create new carbon removal solutions. And I'm very lucky this year to be joined by my co-chair, Sue Dorward, who is going to talk a little bit about the background of the challenge before we introduce our finalist students.
Hi everyone, thank you very much. So we're excited to bring you all 5 teams of students from around the world today. They competed in an extensive competition, and I want to also thank our sponsors. I'm starting off with a lot of gratitude here for 10 Cents Carbon X program for being a sponsor, for Carbon Unbound for donating the tickets for our students and our program staff. To thanks a ton, who was both a financial sponsor and also donated some of their famous carbon removal cards. We got enhanced weathering certificates for our students. Carbon Manager LLC and Possible Studio are our sponsors. Also, for the first time this year, we had, we had a crowdfunding program, and we had a lot of individual sponsors and anonymous sponsors who supported the program, so thank you to all of you. And we also had a team of 30 judges and 15 mentors. We had a program of 8 webinars. This was a webinar we had with 3 of our judges. So a lot of the CDR community is stepping forward and supporting this program and giving students their hard-earned words of wisdom about how to make a successful carbon removal project. And this all resulted in double the participation that we had last year. We had 53 teams register, and we had students from all over the world, including our first team from South America. And we were able to narrow that down through the judging process. The judges looked for quality, but also impact and novelty. So we have some really exciting and innovative projects that the students are going to present. And as I said, we have 5 finalist teams here today that are going to present to you. And their prize for becoming a finalist, being selected as a finalist, was to come here, all expenses paid, to New York City, to Carbon Unbound, to talk with you, to learn about the CDR community, to tell everybody how great their projects are. But I want to thank all of you for taking the time. I know a lot of you have spoken one-on-one with the students, and they really appreciate it. And that's part of the goal of the whole program, is to welcome them into our community, to encourage talented, young, enthusiastic students to enter this field. So thanks to all of you for your support. And with that, we'll hand off to the teams.
As Sue mentioned, we have 5 finalist teams from all around the world. This is an international competition. Before we turn it over to the teams, I just want to take a second to recognize our fellow organizers. Of course, my wonderful co-chair, Sue Dorward. We've got Duncan McDowell, who is our media director, Migran Fu, Adrienne Becerra, Logan Clare, and my co-founder at Open Air, Chris Neidel. So thank you all for your contributions. We would not be able to do this without you. And so without further ado, I will bring up the first team. Please join me on stage, EPFL Carbon.
Hello everyone, bonjour. I'm Alisa André, the president of the EPFL Carbon team. So At our team, we create prototypes, so machines that you can plug anywhere, and with just the push of a button, you can purify the air around you by capturing CO2. We are a team of 60 students, and we have developed 5 prototypes and reached the top 100 of the XPRIZE Carbon Removal Challenge. We come from the beautiful country of Switzerland, and we are at EPFL, one of the top technology and engineering schools, so top 10 in the world and top 5 in Europe. In EPFL, there are a lot of opportunities, and the one that brought us here is in Sion, located in Sion. So there are multiple labs there, and 2 of them are called the LFIM and the LAS. The LFIM works on really advanced adsorbents, and just down the hall, there is a lab working on graphene membranes. So that's the 2 technologies we've been using, and Patrick will tell you more about that.
Thank you. Our hybrid direct air capture module operates with 2 different stages. The first one, Asterix, uses adsorbents to capture CO2 directly from atmospheric air, even at low concentration. Then the adsorbents are heated to release the captured CO2 and generating a 1% CO2 concentration stream. Then, the second stage, EDFX, take advantages of graphene membranes that are atom thin and engineered with atom precise holes. These membranes work like a filter, that allowing only CO2 molecule to pass through and blocking the other gases. The result is a dual output stream, one of purified air, the second one with 95% CO2 concentration. So Estelle now will provide a walk to our prototype.
So the system Patrick talked about was not our first try, and we'd like to show you our progress. So meet Obelix, our very first prototype. Obelix was made to capture CO2 using adsorbents, and as you can see, it had no fancy structure, heat isolation or whatever. But it did not matter because at this point we only needed the proof of concept, and we did obtain it in December 2023 when we captured and released CO2 the way we wanted. So that was the green flag to move on to the next iteration that you can see, with better adsorbent housing, better thermal isolation, less pressure drop. We're very proud to present to you Asterix, which just like Obelix catches CO2 using adsorbents. And 6 months later, we built EDFX, which is our first prototype to have the graphene membranes. We can use it to filter CO2 out of an airstream. And it's the combination of Asterix and EDFX that makes our hybrid prototype. And I'll let Julian tell you more about it.
So we're using 2 technologies, and we're using the optimal range of both techs. Adsorbents favor low concentrations of CO2, and the membranes like higher concentrations. And this enables us to reduce energy to 1,500 kilowatts per ton of CO2, which is about 20 to 30% less than adsorbent-based solutions, reducing costs to $150 per ton of CO2. And I think it must be highlighted as well that this technology is modular. You could put it anywhere and deploy it at multiple scales.
For us, this project goes beyond technology. We wish to spark an interest in students to get involved in carbon capture and create a community around it. We give them the tools to understand the complexity of the field and participate directly into the innovation. One of our goals is also to fill the gap between academy, industry, and students. Our team contains members from very various backgrounds: chemical engineering, mechanical engineering, electrical engineering, robotics, material science, and others. And everyone has their place and purpose in this project.
So we've proven the concept, and we did some tests last week, and we were able to capture a kilogram of CO2 per day. But we don't plan on stopping here. Our goal is bold. We want to capture a ton of CO2 by 2028, so within 3 years. And for that, we're going to capture 100 kilograms of CO2 by the end of next year. And we're going to be focusing on energy consumption, using the adsorbents and finding the right adsorbents for our project, and scaling up the graphene membranes. It's also important for us to continue with this initiative with sustainability in mind, and providing LCAs, making sure that we are scalable and that we don't destroy what we're creating. And if everything goes well, Lausanne will look something like this.
So we would like to thank all our sponsors, so there are a few, and especially thanks Prof. Agraval and Queen, because they help us a ton. But to keep growing in the right direction, we are looking to collaborate with the CDR field. So we are looking for partners, industrial partners, and mentors, if that's possible. So in 3 sentences, we have 2 technologies, 1 mission, and 0 excuses. Thank you a lot.
Thank you, EPFL Carbon team. We're going to take ourselves from Switzerland all the way to Waterloo, Canada now for a team. The university has sent us teams 3 years in a row, 3 carbon removal challenges. They have represented their school in all 3 of them. So please join me in welcoming Team WatAir.
All right, hello Carbon Unbound. We are here to introduce the WatAir system, which stands for Waterloo Algae Integrated Removal, a first of its kind moisture swing, direct air capture and utilization system. Our system operates on a 3-stage cyclic process, which is generally characterized into adsorption, desorption, and utilization. In the first stage, ambient air is blown upwards through a fluidized bed column, with CO2 concentration measuring at the exit point to determine breakthrough analysis. Once the sorbent is saturated with carbon dioxide, we spray deionized water from the top of the column until the sorbent is fully submerged and retained to ensure sufficient desorption. After a set period of time, we pump the deionized water saturated with dissolved carbon dioxide to a separate reactor specially designed to cultivate Chlorella vulgaris microalgae, which uses captured carbon as a growth nutrient. The novelty of our design is generally through 3 different approaches. The first being moisture swing adsorption, which is not a commonly used process, but generally has a lower cost of sorbent, as well as a much safer regeneration process than other form adsorbents. Combined with a fluidized bed configuration, the air to sorbent contact is maximized, which increases capture surface area, as well as has a higher drying capacity, which is a common issue when dealing with moisture swing systems. Finally, to increase the capture efficiency of our process, a specialized pretreatment method is used to apply phosphate ions to our sorbent, which has been shown to have higher capture efficiencies than other moisture swing forms.
The second element contributing to the novelty of our system is the CO2 utilization of growing Chlorella vulgaris algae, which when looking at the global microalgae market presents immense fiscal opportunity in the food production industry. This algae is distinct in its capacity to grow with low power, with low cost nutrients, and without arable land. Moreover, Chlorella vulgaris has a minimal leakage risk and a high photosynthetic utilization efficiency. However, for optimal conversion efficiency, bioreactors need to be used, which introduces a new added maintenance cost.
A main priority of our design this year was developing methods to validate and verify the adsorption capacity of our system. On the screen, you can see 2 different experimental runs from our improved system, which showcase clear and distinct breakthrough curves, which are consistent with available literature and show promise for continued development.
Verifying the utilization stage of our system has come with its challenges, and we've been limited to using our previous designs for algae growth studies. As can be seen, there's a slow rate of change in the optical density of the system water compared to bottled carbonated water, the first being in orange and the second being in blue. However, our team is actively working to develop our design further for further testing.
From an economic standpoint, as well as life cycle analysis, As our team is hosted by the Engineers Without Borders chapter at the University of Waterloo, the aim for this design was to be as low cost and as open access as possible. And for that, we aim for a criteria of a capital cost less than 2,000 USD, as well as operational costs of around 5.5 USD per cycle, around 85 minutes, considering the only material used are electricity and water. From an emissions standpoint, because we need to consider in versus out, for our system, a single point emission from construction is between 15 to 18 kilograms CO2, depending on column materials, as well as a recurring emission of around 14 grams per cycle, contributing to electricity costs based off of the Ontario power grid emissions. Our system is currently at a technological readiness level of 3, as it is a first of its kind system, and we are aiming for improvements in terms of sorbent integrity over a longer period of time, as well as CO2 sensing capabilities and end-use products currently using algae. Current corporate partnerships include a partnership with Haya Reactor Company based out of Waterloo, Ontario, developing a dissolved CO2 sensor for their mini bioreactor platform, but we are open to continued development with other organizations, so please find us at the networking and we'd be happy to explain more. My name is Robert and I am the outgoing team lead for the WatAir team.
And my name is Catherine. I would like to take this time to acknowledge our faculty advisor, Dr. Xiaoyu Wu, for his support on this project, and Laurel Piros Wong, our Engineers Without Borders University of Waterloo chapter president.
I would also like to thank our sponsors, Waterloo Engineering, as well as Engineers Without Border, and another thanks to Experiment.com and the WEEF Foundation at the University of Waterloo for their financial support of this project. Finally, thank you to Carbon Unbound for having us and to the Open Air team for another successful year of the Carbon Removal Challenge.
Our next team actually comes from 3 different universities, Berkeley, Purdue, and Stanford universities. So please give a warm welcome to Electrocean.
Thank you for the warm welcome. We are Electrocean, and we're so excited to share with you our novel solution for carbon capture, energizing reefs to bury carbon. Our solution works by sequestering carbon as limestone, restoring coastal ecosystems, protecting shorelines, and increasing aquaculture yields. First, when examining the current kinds of carbon removals, we found 4 urgent gaps that needed addressing. Carbon market volatility highlights the need for resilience. Specifically, the ability to remain profitable and independent from carbon credit income itself. Next, solutions must be cheap to produce, easy to install, and rapid to deploy. But most significantly, our solutions must work with, help, and aid local communities in order to be widely accepted and adopted. Based on these objectives, we chose to focus on marine CDR. The ocean captures 39% of human CO2 emissions. Marine CDR can remove excess CO2, enabling the ocean to remove more emissions. The ocean itself is also a natural concentrator of carbon. This allows us to bypass the need to specifically concentrate our carbon. It holds 150 times more CO2 per unit volume than air. Lastly, our system utilizes seawater electrolysis to convert marine CO2 into limestone. Then because of this, we durably sequester CO2 for thousands of years to come. The electrified cathode, which accumulates a limestone precipitate, also significantly enhances the growth and survivability of nearby marine organisms that are around and on its surface. Prior studies have shown that this technology, this system specifically, can enhance the growth of shellfish, seagrasses, and corals by more than 150%, as it decreases the energy these organisms need to build their carbonate bodies and also enhances its overall biological energy availability. Lastly, by boosting the growth of these natural reef organisms, we can protect reefs, restoring them actually to protect shorelines, increase aquaculture yields, and build blue carbon storage by sequestering all of this carbon?
Yeah, so based on the science that Faith just described, we ourselves are poised with this technology to capture value from the carbon markets by serving the much larger shellfish aquaculture markets. The reason for that, the mechanism that we're assuming that takes place in is that when an oyster farmer or a shellfish farmer purchases one of our systems, they grow their shellfish more quickly, which allows them to capture more of their own market, which allows us to increase the removals with this technology. We're testing this assumption in our beachhead market, the Chesapeake Bay, which seemed like an ideal spot for market penetration because it underwent a recent ecosystem collapse, and as a result, there is a lot of nonprofit and aquaculture initiatives to get the oyster population back up. And we plan on using the lessons learned from testing these market assumptions in the Chesapeake Bay to expand into the much larger $13 billion market in the US and China to eventually capture as much as we can of the global shellfish market of $55 billion. We also plan on leveraging the wave attenuation capabilities of oyster reefs that we can produce and grow quickly in order to capture the very quickly growing $21 billion coastal restoration markets by rebuilding shorelines with this technology. The way it works is slightly different from the way that, at its root, it's an ocean alkalinity enhancement device. But unlike a lot of the well-characterized OAE systems that are in use today, capturing CDR or about to come online, where they pump the water out and use abiotic methods to remove CO2 and DIC from the water, we have decided to put reactors in situ in the ecosystems so that we can leverage biological feedback loops that allow us to increase the amount of carbon dioxide removal per unit energy input into our reactors. So the way that works is just, one of the pathways is more oysters grown, decreases the turbidity of water, allows seagrass to grow, whereas otherwise it would have been a barren seafloor. That allows us to capture using CDR by ecosystem services, as we call it. And this allows us to leverage the 0.5 gigaton blue carbon sink in the US. So to couple theory with real-life results, we designed a TRL-5 flow-through reactor, which you can see on the screen there, 3 buckets. It allowed us to measure the carbon dioxide removal we get at a baseline with no biological forcing. So we were able to remove 61 grams, or mineralize 61 grams of CO2 in 1 hour at a cost of 105 kilowatt hours per ton of CO2 removed. Using Hampton Roads, Virginia grid factors, where the experiment was run, that was a $19 per ton of mineralized CO2 cost of removal.
So to test the durability of our tech in the field, we also built a floating electrified wave attenuator design. So this prototype, operating at TRL-6, has been deployed for several months, successfully demonstrating its durability in the marine environment and successful wave attenuation and shoreline protection. So the prototype is just like our final product, is low cost and easy to deploy, built from a steel rebar cathode and a commercially available marine float. Okay. So we've been actively coordinating with local shellfish farmers and environmental organizations to see how our technology can integrate into their operations, contribute to their sustainability goals, and assist local communities. We are also creating multiple versions of our in-situ electrolyzer for a wide variety of coastal defense and aquaculture applications. This distributed approach maximizes our impact and ensures we make the most out of the available blue carbon sink. So because we are utilizing multiple CDR pathways, we are currently being conservative with our MRV. As our MRV methods improve, we expect our carbon credit yields to also increase. So we are seeking strategic partners to help us continue developing our technology, non-dilutive and pre-seed funding to help scale up and deploy pilot-scale projects, and referrals to spread the word and increase our impact on CDR, coastal defense, and aquaculture applications. So we would like to thank our mentors, Dr. Thomas Garreau, Mr. Thomas Sarkeesian and Mr. Stephen Delaney for their unwavering support since high school. We'd also like to thank Dr. Dianine Saini and Kat Gomez for their help with this project. We're deeply grateful to OpenAir for this amazing opportunity and to Carbon Unbound for hosting us. So if you would like to reach out to connect with us, you can go to electrocean.eco or scan the QR code. We'd love to connect with you all. Let's build carbon together.
Thank you. We're going to keep things moving right along. We're going to go back to Canada for Western University's Carbon Direct team.
Thanks, Matt. So I'd like you all just to kind of think about this number right here for a second, $2,650. That's how much some small companies in Canada and the United States and across the world are paying for 1 ton of carbon dioxide. I think if I asked buyers on the stage that were on here about an hour ago if they'd pay this much for 1 ton, I'd probably be laughed out of the room and I wouldn't be allowed at this conference again. But there are people that are paying this much around the world right now. Small restaurants, grow ops, agricultural firms, small food and beverage companies, other places like that. And they're being stripped of the money and stripped of the cash they need to help succeed in their businesses. One example of this is a company called Growtown Cannabis. They're located just outside of Ottawa, Ontario in Canada, and they're paying this $2,600 for 1 ton of carbon dioxide. They need this CO2 to help drive performance, increase yields, and improve the cannabis that they're growing to help their business succeed. So this 700 almost kilometer difference between Chatham, Ontario and Kemptville, which is where they source their carbon dioxide from, is what's leading to some of these high costs. By these large transportation costs that they have to get from the Air Liquide facility, it's driving up this cost and forcing bad pricing for them as a company. They are also, in fact, a small user of this carbon dioxide. Compared to some medium and large users that can drive down costs because of large volume discounts, they can't afford these same discounts compared to large suppliers like Coca-Cola or other major growing facilities, and so they have to pay a lot more for their carbon dioxide. But it's not just price that's hurting these companies, it's bad customer service from the established industry. They have to pay extra fees on the tanks they're buying, they have to go through shortages and not get their tanks fully filled when things are going poorly, and they also need high quality and the best prices, which they're not always receiving, even if it's molten cores. So introducing Carbon Capture Direct, our business solution to help make carbon dioxide simple for these small companies. We are proposing to put a direct air capture device that is installed on customer sites to help provide low cost and efficient CO2 to these users while reducing their cost of input to improve their margins as a company. This market can be sized at about $636 million per year, and here's what our technology looks like.
So what you're looking at here is the most recent version of our device. This is our 3rd iteration. We've used low-cost and over-the-shelf components and 3D printing to keep both costs low and implementation quick. The first iteration of our device took us almost a year to build, the second 6 months, and this last one just 1 month. This has worked so far, and we will continue to hopefully speed up our processes. As far as the actual mechanism of carbon capture, we use a temperature swing device that allows us to heat up a zeolite solid-state sorbent that Mateen will tell you a little bit about.
Thank you. So as you can see here, the zeolite 13X sorbent does live inside the chamber, which is wrapped in insulation in the orange section. And on either side of the chamber, there are fans that allow air to pass through. And as the air passes through, the zeolite 13X absorbs the carbon dioxide. So on the right side, you can see our custom extruder. So early on in this project, we determined that 3D printing or additive manufacturing, specifically FDM, is the way to go for creating these sorbents. This is just because we're able to use the layering techniques to create intricate geometries. And the idea here is to use fluid dynamics and mass transfer to be able to maximize the surface area of the sorbent, but also minimize the pressure drop across the chamber, because if the pressure increases, then the fans have to work harder, which uses more energy. So in the center, you can see a waveform structure, which is designed for high airflow. However, Due to the 3D printing technology, we're able to make different geometries to, again, make that balance possible.
Thanks. Yeah, let's switch gears here and talk about the existing market. Most of you are probably used to thinking about CO2 as like an anti-product, but for a lot of companies, it's actually a mission-critical element to their production line. And the problem with that is that, for the most part, it's a byproduct of other systems. So the demand that drives the production of CO2 is not the demand for the CO2 itself. As a result, you have a very volatile supply chain, and specifically, when we're thinking about ethanol, hopefully 10 years from now, ethanol isn't produced. It's major use cases in gasoline for cars, and ideally we live in a world where that's not a thing. But the problem is, there goes 80% of your CO2 production. So we really have to rethink this CO2 supply chain. But even today, there's a beachhead that exists. And Ethan sort of talked about it already, but it's largely that the cost for end users is tied up in this distribution. And when the cost is tied up in distribution, your major players are getting the price of carbon at 200 USD or less. And for the smaller players who don't have the opportunity to build their production locations on site, the ones mentioned by Ethan, they have to operate in place. They don't get the access to that cost savings. Sorry. Yeah, so to summarize, this is already a volatile supply chain. It's going to only get more volatile. And for the people that this volatility hurts the most, they're paying the most. They have the highest willingness to pay. So for a small company like us, where we can come in and make this for a hell of a lot cheaper than the major players can, we think that there's a big opportunity. And really, it comes down to how we provide the service. Your demand is your demand. Sounds great, right? I mean, it's kind of too simple. The energy goes in, you get CO2 out. Yeah, we have some differences in terms of cost if you want cleaner, beverage-ready, food-ready versus, like welding CO2. But for the most part, that's still, even with our V1, which took us a year to build, we were still cheaper than a $100 billion Air Liquide.
So in terms of where we are right now, we've just finished our third prototype. We've completed it. And we've secured a first client at Western University to help provide CO2 to their greenhouses and improve crop yields to help grow their business and show that clean agriculture can work. And in terms of where we're going, we're looking to do a Friends and Family Save $50,000 fundraising over the course of the summer to help complete this minimum viable product that we can then deliver to or execute our pilot project at the University of Western Ontario. So yeah, help us making CO2 affordable, sustainable, and reliable. And we look forward to talking with all of you in the networking session afterwards. Thank you.
And our final team, but certainly not least, that's not how the phrase goes, we are going to welcome to the stage from University of Michigan, Team Terrapump, team of one. Aiden.
Awesome. Thank you, Matt. So I know that I'm keeping everyone from drinks, but I want to thank everyone for sticking around at the end. I'm happy to round out this conference for the sake of everyone in the room. So my name is Aiden. I am a team of one from the University of Michigan, and I am presenting Terrapump is what we're going with. I don't like the name currently, but it's what I had at the time of submission, so this is what we're dealing with. Yeah, wasn't meant to be that funny, but thank you. So really, all we're doing here is we're kind of looking at how to capture carbon in the ocean differently. We're using microbubbles from excess wind and wave power to capture around 25 million tons of CO2 every year at scale without increasing the acidity in the oceans. Before I go any further, I want to first thank the two advisors who don't work on this at all, but were nice enough to be generous with their time. Dr. Josh Jack, who does a lot of work on wastewater at the University of Michigan, and Dr. Jeremy Bricker, who does a lot of work on marine structures and wave power. Just in case anyone doesn't know how abiotic marine carbon capture works, this is basically what we're looking at. We're looking at basically the air is technically acidic and the ocean is technically alkaline. That difference in pH drives the CO2 into the water, and it goes into various different circulation zones depending on how deep it goes, anywhere from 10 years to upwell to about 1,000, even 10,000 years for upwelling, and that's mostly depth dependent. So
in terms of how that actually happens, you have CO2 and it mixes with the water, and you get initially carbonic acid, which we're all pretty familiar with. This is why the oceans are becoming more acidic. Depending on certain factors that we'll talk about in just a second, you can actually get it to go to a carbonate or to a bicarbonate. Anyone that's doing enhanced ocean alkalinity, this is exactly what they're trying to do. They're trying to drive this process to make more stuff go to things that are not acids. But something that I want to do, I want to kind of invite us to think a little bit differently about how this process works. So if you look at what's called the solubility pump, it basically gets worse if the acidity is higher. It also gets worse if the temperature is higher. And it's extremely kinetically slow from a chemicals perspective. So what you're looking at is that as the ocean gets warmer and as it gets more acidic at the surface, it's a negative feedback loop. Things are going to get worse the more carbon there is and the hotter the planet gets, which means that this reaction, the surface is actually the worst possible place to run this reaction, but this is where it's currently being run. And that's really what kind of underpins what we're looking at, is that when you talk about the fact that this is an extremely kinetically slow reaction, most of the air in the atmosphere and most of the water can't react. They can only react at the surface, at that very thin phase barrier. And if you have wind and waves, that can kind of improve the uptake because it disrupts that thermocline where the water's not mixing with the rest of the ocean. But this is a solved problem already. This is a solved problem in wastewater. If you introduce bubbles into the mix, things that are kinetically slow can happen a lot faster. And this is exactly what we're doing. So what we are proposing is to basically force air under the water and release it through a microbubble. When I say microbubble, it's literally just the diameter is around a micrometer in the hundreds. There's also nanobubbles. And what's cool about this is that because you can use excess energy that's already out there through wave and wind turbines, presumably, there's actually no OpEx for energy and there's no OpEx for storage. It's purely CapEx functional. It's a brutally simple equation. So what we're currently focusing right now is the CO2 water kinetics, which have kind of been documented up to this point. Also the sensibility of variables and the sizing of microbubbles. That's a huge factor. And finally, influencing carbonate formation, because that obviously has a huge role in how this would be credit costed ultimately. You may be asking where the best place to deploy this is. There's actually a really great place just outside us right here from where we're standing today. There's a lot of pockets in the North Atlantic that work pretty well for this. And the reason for this is a few things. One, the North Atlantic is quite cold. More interestingly, if you've ever heard of the thermohaline circuit, which you probably haven't, it's basically a massive underwater conveyor belt that moves very deep and very slowly, like thousands of years to cycle the Earth slowly. There are two deep water formations that happen in the North Atlantic. One is just outside of Iceland, and one is roughly around the Brunswick, Nova Scotia area in Canada. And what we think is that this is basically the best place to do what we would call a deep water injection, of trying to get all of these carbonates nice and deep and guarantee, if anyone cares about buying a 10,000-year credit, this is the place to do it. In terms of the best places to do this, since we need infrastructure on the ocean, we think that offshore wind curtailments make a lot of sense. If you're not familiar with offshore wind, they have to dump between about 5 to 10% of their power because of a grid mismatch and the fact that there's no batteries onshore waiting for that power. Since this is just a pump, it's not a catalyst, you can turn it on and off as many times as you want. We can use that power to drive a pump for the duration of the curtailment. That means that you would have a credit break even of around $500 per ton, and you could drive up to 1,000 tons per year from some of the larger wind turbines that are starting to go online right now, the multi-megawatt ones. You can also repurpose oil and gas platforms if you want to. This is slightly more expensive simply because wind power, it's hard to retrofit, as is wave power. And you can also technically use this as a way to do in situ carbon capture storage for currently active ones that are doing flaring and all of that sort of thing. So there's a lot of different on ocean ways of dealing with this. Lastly, let's just talk about the MRV methodology. Obviously, MRV in an open ocean system is historically quite difficult. We think that really the key part of this, a lot of the chemistry has been established. The hard part is just establishing the actual fate of the particles themselves. But we think that that can be done with some pretty strong lab simulations as well, and just some pretty strong CFD. So I want to close out with our development roadmap. We have a partner in Boston who's interested in piloting this with us, the Blue Innovation Labs team, and we're hoping to get a pilot going live soon, but currently we are moving on to lab testing from simulations. And I just want to close by saying thank you all for your time, and we are actively working on that 2028 deployment. Whether it's optimistic or not, time will tell. But we do need anyone that is interested in this premise. If you're working in offshore wind, if you work in oil and gas, we would love to talk to you. We would also love to talk to anyone in the fluids and the marine space, because building anything in the ocean is hard, never mind carbon removal. But that's my email, that's how to reach me, and thank you so much for your time.
That is our showcase for today. I want to take another moment to thank some of our judges, many of whom are in the audience today and helped us. We literally had dozens of experts in the community help us judge and select these projects. If you are interested in doing that or being mentors or helping our teams in any way, employment, funding, please talk to these teams today. If you're interested in helping with the carbon removal challenge in the future, we would love to have more sponsors and partners and people who can work with us to help expand this program. We'd also like to do one more thanks to Carbon Unbound, which really is one of the crown jewels of this competition for our students. So a nice round of applause for Carbon Unbound for this whole conference. And another round of applause for the students. Thank you and good night. Go drink.